Hi, welcome to Nuclear Chemistry. This is part 1 of 3, and today we're going to learn about the 5 types of radioactivity. And we're going to go back to everybody's favorite topic, kinetics, in this chapter. Here are our objectives for today. We're going to learn the 5 different types of radioactivity. We're going to review isotope shorthand notation, which you learned in Gen Chem 1, but you may have forgotten it. We're going to learn the difference between writing a nuclear reaction and writing a chemical reaction. And then we're also going to look at this thing called the magic number and how we can use that to predict radioactivity. So let's start with isotopes. We have a shorthand notation for that. So if I just have element X, I can have a number here and a number here. And so oftentimes you'll see isotopes written this way, or you might actually see them written this way. A here is your mass number, and Z is your atomic number. And these are different. So your mass number is going to be unique to the isotope. Your atomic number is going to be unique to the element. So the atomic number is the number of protons in the element, in this case in element X. So my atomic number, you'll notice, is on this shorthand notation but not on this shorthand notation. But if I know the type of element I have, I can look up the atomic number. The mass number is unique to the isotope, and it is the number of protons plus the number of neutrons. So that is your mass number. And so you'll notice that your mass number is here and your mass number is here. So either one is a perfectly okay way of writing an isotope. So remember, an isotope is an element with a differing number of neutrons. So if I have an isotope of neon, neon has 3 isotopes that occur naturally. Neon 20, neon 21, and neon 22. So these would be the 3 isotopes of neon. I have written them this way so that this is my mass number here. A is going to be equal to 20, A is equal to 21, A is equal to 22. I could write them this way, but in this chapter, oftentimes you're going to see this other notation. And this is the older way that isotopes used to be written, and it's far more informative because it gives you the atomic number right there, which is really helpful to have. So we're probably not going to use this shorthand notation. You're not going to see much of this in this chapter. We're going to look at this shorthand notation primarily. So if I take these and I write them this way, I'm going to have neon 20, neon 21, and neon 22. I'm going to look up Z. Z for neon is 10. So that is the atomic number. Neon is identified uniquely by its atomic number. So if there are 10 protons in this element, then that element is going to be neon. What's going to change or vary are the number of neutrons. So A is the number of protons plus the number of neutrons. So the number of protons doesn't change here, but each one of these has a different number of neutrons. So this one has 10 neutrons, this one has 11 neutrons, and this one has 12. And they all have 10 protons. So these would be isotopes of neon. They all have varying numbers of neutrons. The number of protons is going to remain the same. So this is going to be important because this is going to allow me to determine how many neutrons are in that isotope, because this information is not given on the periodic table. The only thing you see on the periodic table is you see the atomic number, which gives you the number of protons, but unless you have the mass number for that particular isotope, you're not going to know how many neutrons are there. All right, some terminology. We're going to think about things in terms of nuclide, and a nuclide is the nucleus of an isotope. So nuclear chemistry, we kind of have a different language. This would be a nuclide of neon. This would be a nuclide of neon. This would be a nuclide of neon. And these are all going to be very different because they have differing number of neutrons. They're differing weights, right? Because neutrons and protons, remember, have about the same amount of mass, whereas electrons, which is our 3rd subatomic particle, has a really low mass. These are what exist in a nucleus. Electrons are outside of the nucleus. And this slide just kind of sums it up as well. So here's my mass number, here's my atomic number, here's my chemical symbol. Let's talk about writing nuclear reactions. Up to this point, we've looked at chemical reactions. Okay, so when I think about a chemical reaction we write this way. A plus B goes to AB. And what has happened here, this arrow indicates a chemical change has happened. And we define that chemical change by the rearranging of bonds. And so if this is nitrogen, for instance, and this is hydrogen, then I'm going to form ammonia, NH3. I'll balance this guy here. And so what I've done is I've created a new substance by rearranging the bonding of what's happening here. I'm taking this nitrogen, which is triple bonded to the other nitrogen, and it's diatomic, it looks like this, and I'm creating two of these. So in a chemical reaction, I haven't altered my elements in any way. All I'm doing is rearranging the bonding. I start with 2 nitrogen here, I'm going to end up with 2 nitrogen here. I have 6 hydrogen here, I'm going to end up with 6 hydrogen here, but they're going to be bonded differently. Here they're bonded to themselves. Here I've created this ammonia. So this is a chemical reaction. In a nuclear reaction, it's very different. One element is undergoing a nuclear change, and so it's actually going to be turning into a different element, which is something that is only unique in nuclear chemistry. I have an element that's going to undergo a change to become a completely different element. And this is going to happen in the nucleus. So that's why it's called nuclear chemistry, because this change is happening in the nucleus, whereas in a chemical reaction, this change is happening outside of the nucleus. And it's with electrons. So chemical reaction, this bonding is driven by electrons. Electrons are kind of our workhorse of the element. And so when I have a chemical reaction that's happening, what's driving that is the electrons. It's happening outside of the nucleus. In a nuclear reaction, I have an element that's undergoing change. The electrons have nothing to do with it, and this is happening in the nucleus with the protons and the neutrons. And so there's a shifting that's happening in that nucleus where protons are becoming neutrons, neutrons are becoming protons, and that element itself is changing. When this happens, oftentimes when you have a nuclear reaction that happens, the other byproduct of that is I have an energy that's emitted as a result of my nuclear change. I could also have the emission of a subatomic particle. They're going to look different than what we think of in terms of subatomic particles. So it's not going to be emitting a nucleus, it's not going to be emitting a proton, but it's going to be emitting these subatomic particles. These can happen together, or you can have one and not the other. This is called radioactivity. So radioactivity happens when I have a nuclear reaction. I have an element that's going to undergo change to become a completely different element. This is going to happen in the nucleus, and then as a result of that, energy and subatomic particles can be emitted from that element, and that emission of those subatomic particles and this energy is radioactivity. So we're going to cover the different types of radioactivity in this part, and then we're going to do a lot of our calculations in part 2. In a chemical reaction, we could measure the speed of this reaction, and that would be the rate of that reaction. And that could be dependent upon your concentration of both of these reactants, none of these reactants. These could be first, 0, or second order, or some other type of order. And we looked at the rate, and that was kinetics. And in a chemical reaction, my temperature can have an effect on the rate. And remember, we said for every 10 degrees Celsius increase in the temperature, my rate of that chemical reaction is going to double. In a nuclear reaction, my rate is going to be first order for the parent nuclide, and most importantly, temperature is going to have no effect. So we're going to treat these like chemical reactions, and we're going to do things to them. We're going to balance mass, we're going to balance protons, we're going to balance neutrons, and we're going to treat it like a first order kinetic type of reaction. But the big difference there is that temperature has absolutely no effect on the speed of a nuclear reaction. Temperature can help us supply energy to get something going, but temperature is not going to affect the rate here. And so that's vastly different than a chemical reaction, where when we look at the rate of a chemical reaction, that's very temperature sensitive. So these are different. They look the same, we kind of treat them the same, we lump them into to the way that we write a chemical reaction, but it's a very different thing that's happening. It's happening inside the nucleus, not outside the nucleus. It's happening with the protons and neutrons, which up to this point in your chemistry career you've pretty much largely ignored. There are these subatomic particles that live in the nucleus that add mass to your element. The protons pull and keep those electrons in check, but that's really all that we've sort of given them in terms of their role. And nuclear chemistry is all about the protons and neutrons. All right, so our 5 types of radioactivity. The first one we're going to talk about is alpha decay. Then we're going to talk about beta decay. And then we're going to talk about gamma ray emission, positron emission, and lastly, electron capture. So these are our 5 types. And they're all very different. So let's start with alpha decay. What's happening here is I have an unstable nucleus, and it's going to emit a helium atom. And that helium atom is going to be composed of 2 protons and 2 neutrons. So in alpha decay, what's happening is I have an unstable nucleus, and all of these in radioactivity, you have an unstable nucleus. So nuclei that are stable are not going to undergo any sort of radioactivity. So in alpha decay, I have an unstable nucleus, and in order to become stable, it emits a helium atom. It ejects from the nucleus 2 protons, 2 neutrons, and then that stabilizes what we call the parent nucleus, and then it produces a helium atom. That helium atom is referred to as alpha particle. So in an alpha decay, because I'm losing 2 protons and 2 neutrons, my atomic number is going to go down by 2, and my mass number is going to go down by 4. Because my mass number is number of protons plus number of neutrons. So if I'm losing 2 protons, 2 neutrons, my mass number is going to go down by 4. My atomic number is only going to go down by 2 because this is just a measure of the number of protons that I have in that system. So uranium-238 undergoes alpha decay, and it looks like this. This is an isotope of uranium, and it happens to weigh 238, so I'm going to refer to this as uranium-238, meaning that's the nuclide 238 for uranium. It's going to undergo alpha decay, so I could write alpha over my arrow here to indicate that that's what's happening. But if you see the products, then that's also going to tell you what's happening here, because you're going to have predictable products of alpha decay. I'm going to release a helium atom. So this comes out of uranium-238, is this 4,2 helium atom. This is my alpha particle. And I'm going to create a new element. It's going to be what's left. So my mass number has gone down by 4. So this is going to be 234. My atomic number has gone down by 2, so that's 90. I'm going to look up on the periodic table and figure out what 90 is. 90 is this element here. So this is a new element that's been formed, and we call that the daughter element, or the daughter nuclide. So this is my alpha particle. This is going to be my new element. This is the daughter nuclide. This is my parent element or nuclide. So uranium is going to undergo alpha decay. It's going to emit this alpha particle, which is a helium-4, and then it's also going to emit this daughter nuclide here. I need to make sure that my atomic numbers and my mass numbers add up. You'll notice that in order to get to this element here, I took 4 and subtracted it from here. So in order to figure out what your daughter element is going to be, if I'm undergoing alpha decay, then my mass number is always going to go down by 4. My atomic number is going to go down by 2, such that when I add up on the reactant side and the product side, those are going to be equal between my reactants and my products here. I have 92 and 238 on the reactant side, and I have 2 plus 90, 2 coming from here, 90 coming from here. This is my atomic number. That's going to equal 92, so those two match. And I have 4 plus 234 equals 238, so these two match here. So I have set up my nuclear reaction correctly because I haven't lost anything. I've just moved stuff around. So whatever atomic number is I start with, whatever mass number it is I start with, I have to equal that, and it's always going to be sort of the sum of the things that are being emitted in that nuclear reaction. So these must be equal. Just like in a chemical reaction where we don't lose or gain atoms, we just move them around. Here, my Z and my A, my atomic number and my mass number should be the same. I'm just rearranging where my neutrons and protons are and what the radioactivity particle that's coming out of there, what my daughter nuclide looks like. These are all going to add up to equal each other. So that's a good just kind of a check when you're writing these nuclear reactions, just to go back and check and make sure that you've written it right. A few things about alpha radiation. It's the largest of all the particles because this is a large particle here, this helium-42 alpha particle here. This is fairly large. If you think about these things as automobiles, I don't know why, but this would be like the 18-wheeler truck. It's a huge guy that's on the freeway of radioactivity. And so it's the most massive. It's the largest. It has the potential to interact with and damage other molecules by ionizing them. And so the damaging part of radioactivity is the ionizing power of these particles. And actually, alpha particles are super dangerous because they have the potential to ionize sort of anything that they come in contact with. So we say that they have the highest ionizing power, but because they are so massive in size, they have the lowest penetrating power. And so things that like a sheet of paper or our clothing or even our distance away from whatever is emitting that alpha particle is enough for that alpha particle to not be able to penetrate, to get to me. So if I'm a pretty far distance away from something that's emitting an alpha particle, it's going to get slowed down just by the air. So as long as you're not standing really close to something that's emitting alpha particles, you're okay. And I don't think any of us would really want to be that close anyway to anything that's radioactive. So that's an alpha particle. Beta particle is our second type. Alpha is really unique in that nothing is really changing in the nucleus. It's just the nucleus is emitting, like kicking out 2 protons and 2 neutrons. And we'll talk about why that is. But that's a unique type of radioactivity. And everything else, there's going to be some changes happening inside the nucleus. So not just kicking something out, there's a changes happening actually in the nucleus itself. And so beta decay has that. So these are all unstable. So this happens with an unstable nucleus, and it's going to emit an electron. And this is not like a metal losing an electron. That is not what's happening with beta decay. There aren't any electrons in the nucleus. So what's really happening is a neutron is becoming a proton. So in the nucleus, which is where this is happening, a neutron becomes a proton. So protons have a positive charge. Neutrons have no charge. So if you think about a neutron maybe containing a positive and a negative charge, and those balance each other out, and so that's why it's neutral. This isn't really what's happening in a neutron. If you think about a neutron as having the potential to have a positive and a negative charge, it's going to help you kind of keep track of what's happening in this radioactivity. So this will just be kind of our secret way of looking at it. So if I want a neutron to become a proton, that means that I need to lose this negative charge here, which isn't really there. But if I want to have a positive charge, then this is going to go away. That's my electron that's going to be emitted. And so that's going to give this neutron a charge at that point. It was neutral before, now it has a positive charge because it's emitting a negative charge. But it doesn't change its mass. So my mass here is going to stay the same because remember, electrons are very small, so they're not contributing to the mass of a neutron. So if a neutron becomes a proton, its mass essentially stays the same. The only thing that's happening is it's going from a neutral charge to a positive charge. This electron or this negative charge that's being emitted that has no mass. So I'm emitting a negative charge with no mass. That is a beta particle. Our symbol for a beta particle is 0 minus 1e. This 0 means that nothing is changing in the mass. my mass number is number of neutrons plus number of protons. And so if a neutron becomes a proton, I'm still not going to see any change in my mass number. My atomic number is actually going to go up by 1 because now I'm adding a proton to the nucleus. And so my daughter nuclide is going to have 1 more proton in the nucleus than my parent nuclide. So a nuclear equation for this is going to look like, I could have radon 228, and this has an atomic number of 88, and that can undergo beta decay, emit this beta particle here, and now what's going to happen is, because I'm going from a neutron to a proton, my mass number is going to stay the same, 228, but my atomic number is going to go up by 1 because I'm increasing the number of protons. So my atomic number now is 89, and that is this element here. This is my beta particle, this is my daughter nuclide, and this is my parent nuclide. So let's just make sure that our atomic number and our mass number are correct. So remember, my atomic number here is going to go up by 1. It's going to increase by 1. My mass number, I should have no change. So if I look at my atomic number, my mass number between my reactants and my products, my atomic number here is 88, my mass number is 228. Over here, my atomic number is -1 plus 89. So -1 plus 89 is going to give me an 88, and then 0 plus 228 is 228. So no change in A, Z went up by 1. And I accounted for that to add by this beta particle here actually subtracts 1 from this. This is how we're going to represent a beta particle. We could write it just kind of at what's happening. So because it's a neutron that's becoming a proton we can write this way. So it has no protons because it's a neutron, and it has a mass number of 1, because remember, our mass number is protons plus neutrons. So if I'm just looking at a neutron, I would have this symbol here. That's going to go to eject a proton and this beta particle. So this is really what's happening in the nucleus. We're going to look at it in terms of the isotope. So an isotope that undergoes radioactive decay, one of its neutrons is ejecting a beta particle and becoming a proton. And if we were to compare beta particles to alpha particles, beta particles are going to be smaller. So alpha were our 18-wheeler, beta particles are going to be our 4-door sedans. It's much less massive, but that means it also has lower ionizing power. So remember, ionizing power is the ability for this radioactive particle to cause damage. And so a beta particle is going to be less damaging than an alpha particle, but because it's smaller, it has a little bit more penetrating power because it's smaller. But things like metal or thick piece of wood are going to stop a beta particle. So our third one is gamma ray emission. And gamma ray emission is going to be different from alpha and beta particles in that there isn't a particle that's being emitted. This is just the energy. So this is high energy that's going to be emitted during an alpha or beta decay. So oftentimes you'll see gamma also coming off with an alpha particle or a beta particle. You'll have this gamma ray emission, this high energy. And since it doesn't have a mass and it doesn't have a charge, this is going to be our shorthand for a gamma ray. There's no charge, no mass. It's just energy. So because of that, there's no change in my atomic number and there's no change in my mass number. Let's go back to uranium-238. We said that our alpha particle here is helium, and then we're going to produce 234, and I'm also going to have this gamma that could come out. So this is my gamma ray that's also a product of alpha or beta decay. A gamma ray is kind of like your motorbike, like your hot rod. It's the least ionizing, but because it's really small, it's the most penetrating. And so that's why gamma rays are so dangerous, because stopping a gamma ray is going to require several inches of thick lead or thick slabs of concrete. So no longer air or your clothing or even your skin can stop a gamma ray. So that's where when you see people who are trying to ward against radioactivity, they're wearing lead vests, or they are in like a concrete, they have things happening in a concrete bunker. That's to stop the gamma rays. And so the gamma rays are really dangerous for us, because if we are exposed to a gamma ray, it's going to be very damaging because it's able to penetrate into our bodies and ionize whatever it comes in contact with. So our fourth one is called positron emission. And this is an unstable nucleus that emits a positron. Kind of the name gives it away. But what is a positron? A positron is an anti-electron, and it looks like this. So if an electron was 0 minus 1, this is 0 plus 1 e. So that's what a positron is. And a positron is formed when I have a proton that becomes a neutron. So this is the opposite of beta decay. In positron emission, a proton is going to become a neutron. And so for a proton to become a neutron, it's going to emit a positive charge. So there's no change in mass, it's just a charge. This is positive and this is neutral. So I'm emitting that positive charge. So this has no mass and it has a charge. So as a result, my proton is becoming a neutron, my atomic number is going to change, but my mass number is going to stay the same. My atomic number is going to go down by 1. Because now I'm losing a proton in that parent nuclide, it's becoming a neutron. So my atomic number is going to go down, but because my mass number, just because this becomes this, my mass number doesn't change because protons plus neutrons make up that mass number. All right, example of this would be if I had phosphorus 30 undergoing positron emission. I'm going to emit this particle here, this positron. My mass number hasn't changed. My atomic number has gone down by 1, so this is going to be 14. If I look on the periodic table, I see that that is silicon. So this is my positron. Here, this is my daughter, and this is my parent. If I want to do my check here, I can do my Z and my A. I have 15 and 30. This didn't change, so I still have 30. Here I have plus 1 plus 14, so that's going to give me 15. So that my atomic number, my mass number between my reactants and my products has remained the same. Positron emission looks like this. It's very similar in terms of its size, because if you think about what's happening here is it's going to be about the size of that beta particle that's emitted in beta decay. And so it's going to be very similar to beta decay. That was our 4-door sedan. So it's going to have the same sort of ionizing and penetrating power as a beta particle, because the only difference between a beta particle and a positron is the charge of that particle. So this is positively charged. A beta particle is going to be negatively charged. Our last one is electron capture, and it's exactly what it sounds like. This happens when an electron is pulled into the nucleus. This is the only type of radioactivity that doesn't emit anything. In this case, a particle is captured. That particle is an electron. So not adding any mass, but adding a charge in. So what that does is that converts a proton into a neutron, which is what we had in the last one, so there's no change in mass. Mass is the same. This is a positive, this is neutral. But now instead of emitting a positron, what's happening is I'm adding an electron here. So electron is going to be absorbed by the nucleus. It's going to bind with a proton that together is going to form a neutron. So electron capture, my electron I'm going to represent this way. So this is going to be on the reactant side. So it looks like beta decay, but it isn't. It's the opposite of it. And so I'm not decaying, I'm not emitting this particle, I'm pulling it in from the outside of the nucleus into the nucleus. It's combining with a proton to form a neutron. So my atomic number is going to go down by 1, and my mass number is going to stay the same. No change in my mass number. An example of this, if I take Ru, rubidium, 92, and this has an atomic number of 44, if I do electron capture, now this is going to be on my reactant side. My mass number hasn't changed here, but my atomic number has gone down by 1, so this is 43, and this becomes Tc. If I check this Z and A between my reactants and my products, my Z is 44 plus minus 1 is going to give me 43, and I have 43 on this side. This is 92 plus 0 equals 92, and this is 92. So those are the same.